Yourself going down into a black hole, the scariest thing in the world that we know of, a place with such strong gravity that not even light can get away. Weird and stretched out time itself. It is said that anything that falls in is lost forever. Well, that's not really true. What if I told you that there might be ways to make it through this journey, and even more importantly, ways to get back? This isn't a science fiction story. Here we are at the cutting edge of theoretical physics. The answers are even stranger than you thought possible. When we think of black holes, we picture vacuum cleaners in space. Things that are so strong that crossing their limit will destroy you right away. But most people get this wrong. The event horizon, which is known as the point of no return, is not a real surface. It's not a physical wall or a wall of fire. That line is just a statistical limit, a point where escape velocity is faster than light. And this difference is very important. Yes, you would be torn apart by a small black hole long before you got to the event horizon. It would take a lot of force to stretch you into a stream of atoms if your head and feet were farther apart. Physicists use the grimly correct term spaghettification to describe this process. But there's a catch. There are different kinds of black holes. Everything changes around supermassive black holes. Even though these galaxies are millions or billions of times the mass of our Sun, their event horizons are so big that the gravity gradient near the edge is surprisingly weak. The event horizon is the point where nothing strange would happen to a person falling into the supermassive black hole at the center of our galaxy. Not torn or turned into spaghetti, just a quiet journey into the unknown. Take a look at it this way. There isn't much change in gravity between your head and your feet if you're on Earth. It's not something you notice. Now picture Earth being stretched out until it's as big as our solar system. It would be even less of a change in gravity. In a similar way, supermassive black holes work. Because they are so big, their huge gravity spreads out over such a large area that the local effects aren't too bad. At least at first, it is possible to stay alive. Now comes the tougher question. Are you able to leave again? Classical general relativity says that the answer is definitely no. All roads lead back toward the event horizon after it has passed. Space-time points in every direction toward the point of no return in the middle. It's not like you don't have enough engine power to get away, that the idea of outward no longer exists. But at this level, physics gets weird, and weird things can lead to new things. The wormhole is the most well-known possible way to get away. Einstein and scientist Nathan Rosen told the public in 1935 that black holes might not end in singularities at all. Instead, they might link to white holes, which are made-up things that throw away matter and energy instead of consuming them. The path they took together became known as an Einstein-Rosen bridge. You could fall into a black hole in one place and come out of a white hole in a different place on paper. It could be in a different part of our universe, or even in a different universe. What's wrong is security. Einstein said that bridges, if they exist, would fall apart as soon as something tried to go through them. Math doesn't let you off the hook. A single photon would be enough to make the structure unstable. Before you could use it, your escape route would slam shut. But here's where modern physics offers a glimmer of hope. Kip Thorne, a scientist, suggested in 1988 that exotic matter, which is matter with a negative energy density, might be able to keep a wormhole open. It's like the scaffolding that keeps the cave from falling down. A wormhole could be crossed if it had enough strange matter. We have never directly seen alien matter before. It may or may not exist, but quantum field theory doesn't say it can't. Negative energy densities can occur at the quantum level, as shown by the Casimir effect, a measurable effect in which two metal plates that are very close to each other feel an attractive force. Could we ever make enough to keep a tunnel stable? Most likely not, with any tool we can think of right now. The amount of energy needed would be truly out of this world. We're talking about using the power of stars, but the door isn't really shut. That's important. This idea has another possible way out, which sounds even less likely to work, but is based on newer physics. Radiation from Hawking. In 1974, Stephen Hawking made a very interesting guess. It's not always black inside a black hole. They give off radiation, a very slow process that takes an impossibly long time. They go away. impacts close to the event line. In the quantum void, pairs of particles and antiparticles are always appearing and destroying each other. One particle can fall into a black hole while the other gets away. It looks like the black hole is giving off energy from the outside, and this is where things get really serious. That particle that is leaving has data on it. Some interpretations of quantum physics also say that information can never be lost. The black hole information dilemma is what this leads to. Are you really gone if you fall into a black hole? Or does Hawking radiation somehow hide everything about you and send it out into the universe billions of years later? You might not expect a dramatic escape, but in a very real sense, everything that goes into a black hole is lost. The information stays around. Now let's think about something more pressing. Something like survival as we know it. New study into rotating black holes, known as Kerr black holes, shows some surprising possibilities. Kerr black holes don't always end in a point-like singularity like simple black holes that don't rotate do. Instead, they have a more complex internal shape. Instead, they might have singularities in the shape of rings. And now comes the important part. Based on the math, some paths through a spinning black hole might be able to skip the singularity completely. Imagine a cosmic highway that goes through the most dangerous thing in the universe, around the deadly heart and out somewhere else. Where, we're not sure. The equations make it possible to connect to other parts of space-time, worlds, and times. The math becomes strange in ways that make us question what reality is. Does this make sense? Almost definitely not with any technology we have now. We wouldn't be able to come up with a way to make guidance that accurate. Even the smallest variation would lead to obliteration. There is also no way to test these ideas without sending something into a black hole and getting proof of what happens to it. We thought there were absolute barriers, but theoretical scientists keep finding unexpected holes in them. One more option is worth looking into. It fundamentally changes what we think we know about black holes. What if the event limit isn't where we think it is? In 2012, physicist Ahmed Almheri and his friends came up with a strange idea. It's possible that the event horizon isn't even a smooth mathematical line. Quantum effects might make a wall of high-energy particles right at the edge. Anything passing would be burned up right away. If this is true, it would be impossible to stay alive no matter how big the black hole is. But here is the other side of the story. One of the basic ideas behind general relativity is the equivalence principle, which would be broken by a fence. Einstein thought that falling easily in a gravitational field would be like floating in space with no weight. This rule would be broken by a firewall in ways that would make a lot of current physics impossible to understand. There is still discussion, and where there is scientific disagreement, there is room for surprise. What does this mean for us now? We really don't know if people who go into black holes can come back. Physics from the past says no, but quantum mechanics and more advanced theories of gravity make the options very interesting. Unusual matter supports wormholes that can be crossed, raised from the dead through selling radiation, getting through the ring singularities of black holes that are spinning. These aren't made up. These are real areas of study that are being looked into by serious physicists using strict math. There's always the same catch. Current technology can't meet the energy needs. We aren't good enough at engineering to get the accuracy we need, and we can't do any tests. Black holes are the hardest things we can understand. They are at the point where quantum physics and gravity meet. There are two important ideas in physics that still can't fully agree with each other. There will still be some questions that can't be answered until we have a full theory of quantum gravity. But maybe that's the point. We used to think that the speed of sound was unbreakable. We used to think that people could never live in space because of the lack of gravity. We used to think that the atom couldn't be broken up. Every absolute has finally shown the complexity that was there all along. Black holes are the most difficult problem that science has ever had to deal with. The force of gravity is at its strongest with them. They're the places where our math and logic don't work. Still, even here on the edge of what we know, we find signs of doors we didn't expect. Have you ever gone into a black hole and come back out? We don't think so in any future we can think of, but physics has surprised us before. In a world this strange, I wouldn't bet against it either. I hope the video was fun for you. You might want to subscribe if you want to learn more about the strange physics of our world.